Good afternoon, everyone. So welcome to my YouTube channel, मैं Satram. So today we are going to see fifth lecture on direct products. Okay, we were studying internal direct products. Okay, so we will see the result. So I am writing it down. If H, comma K are two subgroups of a group G, such that G is equal to H cross K, then H and K are normal subgroups of G, and G quotient H is isomorphic to K, and G quotient K is isomorphic to H. Okay. So let's prove it. So given G belongs to G, there exists unique H belongs to capital H and K belongs to capital K, such that G is equal to HK. Okay. So we define phi from G to H by phi G map to H. Okay. Since G is equal to HK is unique representation, therefore the map phi is well defined. Okay. So this is well defined map. Okay. Now we'll show that this is homomorphism onto, then by first and its kernel is K, then by first isomorphism theorem of groups, G quotient H will be isomorphic to H. Okay. So this is the idea. So first phi is homomorphism. Okay. Let G1 and G2 belongs to G. Then G1 belongs to G implies करता है there exists unique H1 belongs to H and K1 belongs to K such that G1 is equal to H1 K1. If G1 is equal to H1 K, then what it implies? Then phi G1 will be H1 by the definition of phi. Now G2, similarly G2 belongs to G. This implies there exists unique H2, unique H2 belongs to H and K1 belongs to K such that G2 is equal to H2 K2. Okay. So this implies phi G2 is equal to H2. Okay. Now, what is G1, G2? G1, G2 is nothing but H1, K1, H2, K2. Okay. But we can, by associative property, how we can write this? We can write this H1, K1, H2, H. This is K2 here. K2. Because K1, H2 is equal to H2, K1. Because in an internal direct product, every element of H commutes with every element of K. That is why this is happening. So we can put here H2, K1, K2. Okay. Now we can write this by associative property like this. Okay. Now, but this representation is unique representation of G1, G2 is unique. So this implies phi G1, G2 is equal to H1, H2. But H1 is phi G1, H2 is phi G2. Okay. So this implies phi G1, G2 is equal to phi G1, phi G2. So this implies phi is homomorphic. Now second, phi is onto. Let H belongs to H. Then we can write, then put G is equal to H E belongs to G. So we should write here, then G is equal to H E belongs to G and phi G is equal to H. Okay. Since G1 H belongs to H, there exists G belongs to G such that phi G is equal to H. So this implies phi is on to. Since now phi G to H is homomorphism onto by this is homomorphism onto by first fundamental mental theorem of first fundamental theorem of groups, or you can say homomorphism. So first fundamental theorem on homomorphism of groups. Homomorphism of groups. We have G quotient kernel phi is isomorphic to H. Okay. Now, what is kernel now? Next, what is kernel of phi? Kernel of phi is equal to G belongs to G such that phi G is equal to identity. Okay. Now, you take any element, so this will be equal to. So if first element is identity, then we know that every element. So what will be? G is of the form H, K. Okay. Okay. So what does it mean? It means that phi. So what does it mean? It means that H belongs to H and K belongs to K, such that and phi G is equal to E. Now, what is this? This is equal to GH. Okay. Now, what is this? This is because by definition of phi G, it should be H is equal to E. Okay. Now, H belongs to H and K belongs to K and H is equal to E. H is equal to E. If H is equal to E, then G, E, K. Now, this H is fixed. So, K belongs to K, I can write. Okay. So, this is equal to G is equal to K such that K belongs to capital K. So, I can write there. So, what is this? Now, I am taking, okay, G is equal to HK. So, it means I can write it K such that K belongs to K. Now, what is this? What is this? Nothing but K. Okay. So, kernel is actually K. Kernel is K. Okay. So, since K is kernel of phi, therefore, K is normal subgroup of G. Okay. Now, by first, we have what we have? We have G by kernel phi is isomorphic to H, but kernel of phi is nothing but K. So this implies G quotient K is isomorphic. Okay. So hence K is normal subgroup of G, and G quotient K is isomorphic to H. Okay. Similarly, we can show that we can show that H is normal subgroup of G, and G quotient H is isomorphic to. Okay. So this theorem is proved. So today's lecture up to this, if you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.